In this video, we're going to go over a very common torque problem that has to do with a ladder. In the first few minutes, we're going to quickly review our steps for approaching torque-related problems, and then the rest of the video will spend on solving this very important problem. So let's take a look firstly at our steps. So as always, the first step is going to be to draw a free body diagram. Ask ourselves what forces are present here, and let's label those forces with the arrow up, down, left, and right. We'll have to choose a coordinate system. Typically, clockwise direction means negative, and counterclockwise is positive. Now, we also have to identify the rotational point. If the system is not rotating, you can pick any point as your point of rotation. And since torque is equal to force times distance, right, you need to find the distance of each of those forces from the pivot point that you picked in the previous step. Just like in the unit of forces, you have to sum up all your forces in the horizontal, in your vertical direction, and set them either to 0 or ma, depending if there is acceleration or not in the system. Finally, you also need to sum up all your torques, right, and set the sum of torques equal to I times alpha, or moment of inertia, times angular acceleration. Then you'll have three equations, the two second Newton's law equations in the x and the y direction, and the torque equation. And then from those three equations, you can solve for whatever unknown that the problem is asking. So let's take a look at how these steps apply to the following problem. Here we have a ladder. A uniform ladder of length L and mass m leans against a smooth vertical wall, making an angle theta with the horizontal ground. The bottom of the ladder rests on a rough horizontal ground with the coefficient of static friction mu. Find the expression for the minimum angle theta in terms of the coefficient of static friction. So essentially we need to find the expression for theta, right, in terms of all these variables that are given. Fantastic. So as always, the first step, let's label the forces that we have here. So of course, we're going to have a force. Now we're making this diagram, right, for the ladder itself. So there's going to be a gravitational force as always, right, from the ladder. Now, it's also in the contact with the wall over here. So the wall is pushing it away. So therefore, there's going to be the normal force. Remember that the normal force is always directed at 90 degrees to the surface. So the force from the wall is going to be directed like here. Similarly, the normal force from the ground is going to be directed at 90 degrees to the ground. Now, it says that the wall is smooth, therefore there's not going to be any friction here. However, the ground is rough, therefore there will be friction. Now let's think in which direction the friction is going to be pointed. Friction is always pointed opposite to the direction of motion. So think about, where does this ladder wants to move? It wants to slide down, right? Therefore this wants to move to the right. Therefore the friction would be pointed to the left over here. So over here would be force of friction. Great. Now let's write down this would be our horizontal, right, axis would be left, right, our vertical would be up, down. So let's write down the second Newton's law in the x direction. So which forces are horizontal? In this case, it's going to be this force F and this force N, right? N is to the right and F is to the left, and they're equal to 0 because this ladder is not accelerating. So N of the wall is equal to force of friction. What about in the y direction? In the y direction, I have these forces left, normal force from the ground and mg. So N F net is equal to ma. So Ng minus mg is equal to, again, 0. This ladder is not accelerating, or normal force from the ground is equal to mg. Now, of course, we also need to write down our torque equation, right? That's the third step. So sorry, misspelled torque here. Now, the torque equation is going to be the following. We can pick the moment of rotation, right? Since we essentially, since the ladder is now rotating, right, we can pick any point as the point of rotation. Really, there's only 3 points to consider, either this one, or this one. Now, the most beneficial point of rotation is going to be the one that will cancel out the most unknown forces possible, right? So I don't know this normal force, I don't know this normal force, and I don't even know this force of friction right here. So if I'm picking between, so first of all, it doesn't make sense to pick the middle, right? Because I know mass. It makes sense to pick either this or this point. However, here there's two unknown forces. So I think it's better to pick this as the point of rotation. So pick bottom point as the point of rotation. Cool. So therefore, if we pick this bottom point as a point of rotation, right away the distance of ng is 0 and the distance of friction force is 0. So those torques already canceled out, right? Now let's think about the rest of these forces. So mg, we have essentially mg and nw. Great. So let's start with nw, right? So we have to consider torque from nw. So firstly, you have the force itself, nw. What about the distance away from the point of rotation? The distance away will be just the length of the whole ladder, which is L. Okay. Let me just fix this. Then sine of the angle between the axis of rotation, which in this case is the ladder, and the force. So what we're looking for is this angle, which as you can see is going to be equal to this angle theta, right? Because they're essentially corresponding angles, right? So this angle is going to be equal to this angle, theta. So sine of theta. So that's expression for the torque of the normal force. What about the gravitational force? All right. So now the force itself is going to be mg. It's applied at distance of L over 2 from the rotational point, right? And what about the angle? So let's zoom in right here when we talk about the angle. So the angle that mg is going to, the angle is theta, is the angle between the force and the axis of rotation over here. So that's what I'm looking for, right? And the angle I want to find it in terms of angle theta. So therefore, this angle right here will be, because this is a right triangle, this angle right here is going to be 90 minus theta. So it's going to be sine of 90 minus theta, which, by the way, I can write sine of 90 minus theta as just cosine of theta, right? This is one of the trick formulas that you can write sine of 90 minus theta as cosine theta. All right, so we have both of the torques. Therefore, net torque is equal to, again, 0 because it's now rotating. So NWL sine theta, torque from the normal force, minus torque from the gravitational force, mgl over 2 cosine theta, is equal to 0. All right. Let's take a look. So what I can find from here is NW. My L cancels out. I can put mg cosine theta on the right hand side, and I can divide both sides by sine theta. So 1 over half mg. Cosine over sine will be cotangent theta. Great. So I just found my normal force, but what I needed to find was the angle, right, in terms of coefficient of friction. So how can I relate it? Let's come back to these equations because we haven't actually used them yet, right? We have this equation right here that the normal force from the wall is equal to the frictional force. So let's set this equal to the frictional force. And the frictional force is equal, as we know, the formula is mu times n. And in this case, n of the ground is mg. one more time, right? The frictional force, I feel like I went over that a little fast, right? So we said this normal force from the wall is equal to this equation we just derived from the torque. However, this equation right here says, right, that we said in the very beginning, said that the frictional force is equal to the normal force from the wall. Now, I'm just writing out what the formula for the frictional force, which is mu times n of the ground, right? And the n of the ground, we're bringing this equation into action, is going to be mu times mg. So, canceling out m and g from both sides, I have cotangent of theta is equal to mu over 2. Prefer to write, let's say, instead of cotangent, let's rewrite cotangent in terms of tangent. So, or flip both sides. And since we're looking for the angle, right, I'm going to take inverse tan of both sides to find my final answer over here. So let's check. 2 over mu. Fantastic. Let me just double check this. So tangent theta is equal to so we made just a little error right here. I apologize. So right here, when we were rearranging this equation, right, we had 1/2 cotangent theta is equal to mu. Therefore, we multiply both sides by 2. So if we want to write it in terms of tangent, right, we need to do 1/2 inverse both sides. So tangent theta is equal to 1 over 2 mu. Or theta is equal to, I apologize for this error, right? So just like this, we solved our probably more complicated, right, or most complicated problem in torque, right? Now, in the next video, we're going to go over rotational momentum and rotational kinetic energies. So make sure that you watch those videos if you want to be an expert in basically the unit of rotation. As always, thank you guys for watching. Keep practicing and keep watching these videos on your way to an A.